Hello everyone, welcome to solve this math Olympiad algebra problem, and here we have 1 to the power of n equals to 5, and we solve this problem for the values of n. So the very first step we are going to do is here first we take the log on both of the sides of this equation, so that when we take log it will be written as log of 1 to the power of n equals to log of 5. And after that here we use the property of log and we move this n to the front of this log, and it will be written as n times of log 1 equals to log of 5. And now we move this log 1 to the right hand side, and it will be written as n equals to log of 5 divided by log of 1. So here we know that the value of this log 1 is equals to 0. It means that this is some constant and something over 0 is not exist. So it means that this in this question this question does not exist an real root. So here we have there is no real root. So we have no real root in this question. So now we need to find the complex or imaginary roots. So that here we use the nice Euler's identity, and you know that about Euler identity, e to the power of iota theta equals to cos of theta plus iota sine of theta. So this is called the Euler's identity. And now first we check, is this Euler identity hold for the value of theta equals to 0. So when we put theta equal to 0 in this equation, it will be written as e to the power of iota into 0 equals to cos of 0 plus iota sine of 0. And here we know that the value of cos 0 is 1 plus the value of sine 0 is 0. So it means that the value of e to the power of iota of 0 equals to 1. So now we write the Euler's identity in general form. So the general form of Euler identity is written in this form: e to the power of 2k pi iota is equals to cos of 2k pi plus iota sine of 2k pi. So this is called the general form of Euler's identity, and here we have the value of k is over 1 2 3 and up to so on. So now we first we check we check the behavior of this Euler's identity for different values of k. So that here first we put the value of k equals to 1. So when we take k equals to 1 here, it will be written as e to the power of 2 pi iota is equals to cos of 2 pi plus iota sine of 2 pi. Okay, so this is the our value. So now here you see that the value of cos 2 pi is equals to plus 1, and the value of sine 2 pi is 0. So it means that the value of e to the power of 2 pi iota is equals to 1. So here you remember one thing about these values. So if you have a cos of some even multiple of pi, so it will gives us the value is positive 1, or if we have the sign inside the even multiple of pi, so it is always gives us the 0 value if it is even or odd. So here this e is denote the even number. Okay, so if you have even number of pi, it will be gives us cos will be gives us positive 1, and sine is gives us the value is 0. So now we substitute here k equals to 2 in the above generalized form of the Euler's identity. So first we put k equals to 1, and now we substitute here k equals to 2. So when you put k equals to 2, it will be written as e to the power of 2 pi iota is equals to cos of, so sorry, this will becomes 4 cos of 4 pi plus iota sine of 4 pi. So here we know that the value of cos 4 pi, which we can always define here, if you have cos even multiple of pi becomes plus 1 and sign will gives us the value is 0. So here we have the value of e to the power of 4 pi iota is equals to 1. So this is the value of e to the power of 4 pi iota, and now here we substitute or we check it for k equals to 3. So when we substitute k equals to 3, so we have e to the power of 6 pi iota is equals to cos of 6 pi plus iota sine of 6 pi. So here again we have the value of this is 1 and the value of sine is 0. So we have the value of e to the power of 6 pi iota is equals to 1. So this shows that if this shows that the value of all multiples of pi is equals to 1, because at k equals to 3 we have the value of Euler's identity is 1, for k equals to 2 we have Euler's identity 1, and for k equals to 1 we again have the Euler's identity equals to 1. So we generally say that the value of e to the power of 2k pi iota is equals to 1 for some values of k equals to 1, 2, 3, 4 and up to so on. So if we have the value of e to the power of 2k pi iota equals to 1, and now here we need to take the nth power on both of the sides. So when we take the nth power on both of the sides, it will be written as e to the power of 2k pi iota and its whole power n equals to 1 to the power of n. And now in the given question statement, we have the value of 1 to the power of n is equals to 5. So here we have the exponent to the exponent. So these exponents are multiplied by each other, and here we get it e to the power of 2k pi n iota is equals to 5. So because in this question we need to find the complex value of this n, so that here we take the log on both of the sides. So we take log and it will be written as e to the power of 2k pi n iota is equals to log of 5. So now here we move this exponent to the front of this log and it will be written as 2k pi n iota into log of e is equals to log of 5. So here we know that the value of this log e is equals to 1. So 1 is multiplied by this whole term and it will be again equals to 1, and we written as 2k pi n iota is equals to log of 5. So because we solve this problem for the value of n, so we move all these terms to the right hand side and we get the value of n equals to log 5 divided by 2k pi iota. So this is the final answer of this question, and here we have our k equals to 1, 2, 3 and up to so on. So this is the final answer, and thank you so much for watching this video. Please subscribe to my channel for more exciting videos.